Imagine this. You're standing in your kitchen. A cup slips from your hand. It falls. For a split second, there's silence, and then, crash. Porcelain explodes across the floor. Shards slide outward. Some pieces spin. Others stop instantly. The sound echoes longer than it should, like the room itself knows something final just happened. Now don't move. Just sit there. Wait for it. Wait for the fragments to twitch. Wait for the pieces to lift themselves off the ground. Wait for them to spin backward through the air, clicking perfectly into place, until the cup reforms in your hand whole, warm, untouched. You can wait for hours, days, years. It's not going to happen, and the strange thing is, you don't even need to test it. You already know. Everyone knows. There is no suspense here, no mystery, no doubt. But why? Why are we so certain that broken things don't break? That waves crash but never uncollapse. That smoke spreads through a room but never politely gathers itself back into the cigarette? Think about standing by the ocean. A wave rises, curls, and crashes into white foam. The foam spreads chaotically across the shore. Now imagine waiting for that foam to collect itself, to draw inward, to rise gracefully back into a perfect glassy wave and retreat from the sand. It would be beautiful. It would be cinematic. It would also be absurd. In physics lectures, there's a classic demonstration. A video plays, water splashing, glass shattering, people jumping into pools. Then the footage runs backward. Suddenly, the chaos rewinds. Water leaps neatly back into a glass. Shattered glass pieces reassemble midair. A diver shoots backward out of the pool, water forming a perfect column beneath him. And the room laughs, not because it's funny and a joke sense, but because something deep inside us rebels. Our instincts reject it. We recognize immediately. This is wrong. This doesn't belong to reality. That laughter is powerful. It reveals something fundamental. We don't just observe that the world behaves one way. We feel that it must behave that way. But here's where it gets deeper. This isn't just about cups or waves. It's not just about physical events moving in one direction. It's about something far more intimate. It's about time itself. Because even without experiments, without slow-motion footage, without physics equations, your own inner experience already knows the difference between past and future. You remember yesterday. You don't remember tomorrow. You can recall a conversation that happened an hour ago in vivid detail, the tone, the expression, the exact words. But you cannot recall next week's conversation, even though, in some sense, it is just as real in the unfolding of the universe. The past feels fixed, solid, locked in place. The future feels open, unwritten, flexible. That asymmetry, the difference between what has happened and what has not, is so deeply embedded in our consciousness that we rarely question it. But here's the unsettling truth. At the fundamental level of physics, most of the basic laws don't actually care about direction. If you take many equations that describe motion, gravity, electromagnetism, even quantum interactions, and you run them backward in time, they still work. The math doesn't protest. So, if the microscopic laws are mostly reversible, why does the world we experience feel so stubbornly irreversible? Why do eggs scramble but never unscramble? Why does heat flow from hot to cold but never the other way around? Why does order decay into disorder but never spontaneously rebuild itself? Why does the past feel carved in stone, while the future feels like fog? That's not just a scientific question, it's a philosophical one, and it's personal. Because this one-way flow isn't limited to physics. It defines your life. Childhood becomes memory. Words, once spoken, can't be unsaid. Decisions ripple outward permanently. Every moment collapses into history the instant it passes. You can break a cup in a second. You cannot unbreak it in a lifetime. So, what is this invisible rule? This law that governs not just matter but experience? What is this arrow that points from yesterday to tomorrow and never bends backward? To understand that, we have to go deeper than shattered porcelain. We have to look at the hidden principle that quietly shapes everything around you. The principle that explains why the pieces never jump back up. And once you see it, you'll never look at time the same way again. We remember yesterday. We do not remember tomorrow. That simple fact feels so natural that we almost never question it. You can close your eyes right now and replay something from your childhood: the smell of a classroom, the sound of a familiar voice, the color of the sky on a certain day. The past is stored, layered, archived inside you. But try this instead. Remember next Tuesday. You can't. You can imagine it. You can predict it. You can worry about it. You can hope for it. But you cannot remember it. Psychologically, the past and the future are built from entirely different materials. The past feels solid, recorded, fixed. The future feels open, fluid, adjustable. We talk about regret but never about regret. We feel remorse about what we've done, but we feel hope about what we might do. We believe deeply that we can act now to shape what's coming. Yet almost no one believes they can act now to rewrite what has already happened. You might wish you had said something differently. You might replay the moment in your mind. But no matter how strong the regret, the past doesn't budge. It's sealed. Now here's where things get interesting. Everything around you, your body, your brain, your memories, is made of atoms. Tiny particles obeying precise physical laws. The same laws that govern stars, oceans, and falling cups govern the neurons firing in your mind right now. So, if both you and the world are made of atoms, and those atoms follow physical rules, then this deep psychological difference between past and future must come from somewhere inside those rules, right? It seems obvious. If broken cups don't break, if we remember yesterday but not tomorrow, if waves don't uncrash, then surely the laws of nature must themselves favor one direction. Surely somewhere in the machinery of the universe there is a built-in bias, a rule that says, forward only. You would expect to find, buried inside the equations of motion, a one-way valve, a principle that pushes reality from order toward disorder, from structure toward chaos. You'd expect physics to say, this direction is allowed, that direction is forbidden. But here's the shock. We haven't found it. As far as we can tell, most of the fundamental laws of physics do not care about direction. If you take the equations describing motion and flip the sign of time, replace forward with backward, the mathematics still works. The equations don't complain. They don't break. They don't suddenly become nonsense. In principle, the microscopic interactions between atoms could run either way, which means something unsettling. If you filmed atoms colliding, bouncing, attracting, repelling, and then ran the film backward, the reversed version would still obey the same physical laws. The physicist watching it, at least at the microscopic level, shouldn't laugh. And yet, we do laugh when we see broken cups reassemble. So, where does the difference come from? If the laws themselves are neutral, if the equations are symmetrical, why does reality feel so asymmetrical? Why does time feel like an arrow instead of a loop? To explore that, let's look at something concrete, something foundational, one of the cleanest and most beautiful laws in physics. Let's take gravity. Imagine two objects floating in empty space. According to Newton's law of gravitation, they attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. Simple, elegant, predictable. Now imagine watching them move under that force. They drift closer together, accelerating as they approach. Eventually they collide. Fine, but now imagine running that same motion backward. After the collision, the two objects separate. They move apart, slowing down as distance increases. Does that violate gravity? No. The backward version still perfectly satisfies the same equation. The law of gravitation doesn't say move forward in time, it simply relates positions, velocities, and forces. It works both ways. So, gravity doesn't give us our arrow of time, and neither do most other fundamental forces, which leaves us with a puzzle. If the basic rules don't prefer the future over the past, if the microscopic film plays correctly in both directions, then why does the large-scale world, the world of cups, waves, memories, regret, refuse to reverse? Somewhere between atoms and experience, something changes, and to see it clearly, we have to zoom in carefully, step by step, law by law, because the answer isn't hiding in a single force. It's hiding in statistics. And once you understand that, shift from strict laws to overwhelming probabilities, you'll begin to see why the universe moves the way it does, and why you can remember yesterday but never tomorrow. Picture this: a star massive, steady, burning at the center of a quiet solar system. Around it, a planet moves in a smooth ellipse, not a perfect circle, an elegant oval. It speeds up as it gets closer to the star, slows down as it drifts away, and as it moves, an invisible line from the star to the planet sweeps out equal areas in equal times, like a silent geometric rhythm. Now imagine filming that motion. You let the planet travel along its orbit, frame after frame, until it reaches some distant point along the ellipse. Then you press rewind. The planet begins to retrace its path. It curves gracefully in the opposite direction. It speeds up and slows down at exactly the right moments. The same areas are swept out in equal times, only now in reverse order. And here's the strange thing. Nothing looks wrong. There is no awkwardness, no physical absurdity, no sense of impossibility. The backward motion satisfies the law of gravitation just as perfectly as the forward motion did. You could not tell which version was real just by looking at the orbit. Gravity doesn't care. To put it more sharply, if, at a single instant, you could magically reverse the velocity of every particle in a system, flip every motion like a mirror, then the entire system would begin to unwind. Every collision would uncouple. Every interaction would retrace itself. Every path would be followed backward with perfect precision. If particles had tangled themselves into a complex dance over time, reversing all their speeds would cause them to dance backward through the exact same steps. The universe would unscramble itself, not because it wants to, not because it remembers, but because the laws governing motion are symmetric in time. Gravity works the same way forward or backward. And it's not just gravity. The laws of electricity and magnetism, time reversible. The equations describing nuclear forces, as far as we know, time reversible. Even many processes in particle physics. When you examine the equations carefully, don't build in a preferred direction. Mathematically, time has no arrow. If you take the equations and replace time with negative time, they still stand. Now, there is a subtle footnote. Certain rare processes, like aspects of beta decay, have shown hints that nature might contain very small asymmetries. There have been experiments suggesting that some interactions may slightly distinguish between past and future. But here's the crucial point. Even if that's true, those effects are extraordinarily tiny. They don't control the everyday world. They don't determine why eggs scramble. They don't explain why cups shatter or why you remember yesterday instead of tomorrow. For almost everything you see in daily life, the fundamental laws are effectively time reversible. So we are left with a remarkable tension. At the deepest microscopic level, the equations allow the universe to run either way. Yet at the macroscopic level, the level of planets, oceans, kitchens, and human memory, everything seems locked into one direction. The planet's orbit looks fine reversed. The shattered cup does not. If reversing every particle's velocity would, in principle, make the world unwind, why don't we ever see it happen? Why don't we observe rooms spontaneously reorganizing themselves? Why don't smoke particles gather back into cigarettes? Why don't spilled liquids climb neatly back into glasses? The laws permit it, but reality never chooses it, and that tells us something profound. The arrow of time is not written directly into the fundamental equations. It emerges from something else, something statistical, something about how many ways things can be arranged. Because while it is possible under the laws for all particles to reverse their velocities exactly, the odds of that happening spontaneously in a system containing trillions upon trillions of atoms are so unimaginably small that, for all practical purposes, it never occurs. Not forbidden, just overwhelmingly unlikely. And in that gap between what is allowed and what is probable, the arrow of time is born. So, to understand why the planet's orbit can run backward without absurdity, but the shattered cup cannot, we have to stop thinking only about laws. We have to start thinking about numbers. about order and disorder, about the difference between a few special arrangements and an almost infinite sea of messy ones. That's where the real story begins. The fact that I'm speaking to you right now has nothing to do with rare particle decays. It depends on chemistry, on electricity flowing through neurons, on air molecules vibrating as sound leaves my mouth and travels outward. And notice something simple. When I speak, the sound spreads into the room. The air carries it away. It does not suddenly reverse direction, gather itself neatly from the corners, compress into a wave, and dive back into my mouth. That doesn't happen, and we cannot blame that on some tiny asymmetry in beta decay. The ordinary world, the world of voices, footsteps, sliding objects, ocean tides is governed overwhelmingly by laws that, at their core, are time reversible. So, if the equations allow reversal, why does reality refuse it? Let's look closer. Take the Earth itself. It spins on its axis day after day, but careful measurements show something subtle. The rotation is slowing down, very slightly, over long periods of time. Why? Tidal friction. The gravitational pull of the moon raises tides in Earth's oceans. Those tides slosh. They rub against coastlines and the ocean floor. That rubbing friction converts organized rotational motion into tiny random motions of molecules. Heat and friction feels irreversible. Push a heavy block across the floor. It slides, it slows, it stops. Now stand there and wait. It does not suddenly begin sliding again, accelerating smoothly back into your hand. Friction seems to break the symmetry, but look deeper. Friction isn't a fundamental force. It's the result of unimaginably complex interactions between trillions of atoms. When the block slides, its orderly motion, the coordinated movement of the whole object, is transferred into disorganized microscopic motion inside the wood and the block itself. The atoms jiggle. They vibrate randomly. They wiggle-waggle, as it were. Orderly motion becomes disordered motion. The block's smooth glide turns into microscopic chaos. And here, right here, is the clue. Because nothing in the fundamental laws forbids the reverse. In principle, if every single vibrating atom in the floor just happened to jiggle in exactly the right, coordinated way, they could push the block forward again. The microscopic chaos could reconverge into organized motion. But think about what that would require. Trillions upon trillions of atoms would need to coordinate perfectly, instantly, spontaneously. Not impossible, just absurdly unlikely. Let's take a cleaner example. Imagine a tank of water divided into two halves. On one side, clear water. On the other, blue water mixed with ink. A thin barrier separates them. At first, everything is tidy. Blue on the left, white on the right. Now gently remove the divider. Now zoom in. closer, closer still, until the smooth blue color of the water disappears, and all you see are individual molecules, tiny particles in constant, frantic motion. They jitter, they collide, they ricochet in every direction. Thermal motion never rests. It's chaos at the smallest scale. At the beginning of our experiment, most of the blue molecules are on one side of the tank, and most of the clear water molecules are on the other. A neat separation, order, but nothing is holding them there anymore. They jiggle, they bump, they wander, and because there are not just thousands but billions upon billions of these particles, the odds are overwhelming that, through their endless random motion, they will gradually intermingle, and that's exactly what we see. The blue spreads, the boundary dissolves, the system drifts toward uniformity. But now do something very specific. Don't watch the whole tank. Pick one collision, just one. Here's a blue molecule moving northeast, a clear water molecule drifting southwest. They approach each other, they collide, they bounce apart at new angles. Perfectly ordinary. Now rewind just that tiny segment of film. The two molecules approach each other from those new angles, collide, and depart along their original paths. A physicist examines it carefully, measures angles, checks speeds, applies the equations. Everything works. The laws of molecular collision are perfectly reversible. If molecules approach in one configuration, they scatter in a predictable way, reverse their velocities, and they retrace their paths exactly. At the level of a single event, nothing breaks. Now expand your view again to the whole tank. In the forward movie, you begin with separation and end with mixing. That makes sense to us. It feels natural. In the reverse movie, you begin with a perfectly uniform mixture, blue and white, evenly distributed everywhere. Then, as time progresses backward, something astonishing happens. Through countless collisions, the blue molecules gradually collect themselves to one side, and the clear molecules gather to the other. It looks absurd, unnatural, almost magical. And yet here's the unsettling part. If you analyze every single collision in that reverse film, each one obeys the laws of physics flawlessly. No rule is violated. No equation is broken. So where does the absurdity come from? It comes from the pattern, from the overall arrangement. When you start with a special arrangement, blue on one side, clear on the other, and let random motion take over, the system almost inevitably becomes more uniform. There are vastly more mixed arrangements than separated ones. But if you start with a uniform mixture and allow random motion, the odds that those random jiggles will accidentally conspire to create separation are astronomically small. Not impossible, just unimaginably unlikely. It's not against the laws of physics for the molecules to bounce around in exactly the right way to unmix themselves. It's just that the number of coordinated right ways is microscopic compared to the number of messy, mixed ways. Think of it like shuffling a deck of cards. There is exactly one arrangement that counts as perfect order, but there are trillions upon trillions of arrangements that look random. Shuffle the deck once, and it almost certainly becomes disordered. Keep shuffling, and it doesn't suddenly snap back into perfect order. Could it? Yes. Will it? Not in a million years. And that's the key. Irreversibility is not about what is allowed. It's about what is overwhelmingly probable. The laws of physics don't forbid the blue from separating. They simply don't favor it. Going from order to disorder is statistically natural. Going from disorder to order requires an extraordinary coincidence, an almost miraculous alignment of countless microscopic motions. So when we say the world is irreversible, what we really mean is this. One direction is likely. The other direction, while technically possible, is so staggeringly improbable that we will never witness it. The cup could unbreak, the smoke could unspread, the dye could unmix, but the universe would have to arrange trillions of particles into precisely the right configuration at precisely the right instant. And that is why you can wait forever for the pieces to leap back into your hand. Not because nature forbids it, but because nature plays the numbers, and the numbers are not on your side. It would be ridiculous to sit beside a perfectly mixed tank of blue water and expect that, if you just waited long enough, the restless jiggling of atoms would politely sort themselves out, again drifting to one side, clear water to the other. At least ridiculous for the kinds of systems we actually deal with. Now, imagine something smaller. Suppose instead of trillions upon trillions of molecules, we had only a handful 4 or 5 atoms in a tiny box. They bounce around randomly. Given enough time, it's not crazy to imagine that, purely by accident, they might momentarily return to a configuration close to where they started. Order could reappear briefly. With small numbers, strange coincidences are believable. But that's not our world. Our world contains not for atoms, not for million, but something closer to 4 or 5 million atoms in even a simple glass of water. And when numbers get that large, probability becomes merciless. Yes, it is technically possible for every single molecule in a uniform mixture to wander, by chance, back into a perfectly separated arrangement. But the odds are so staggeringly small that the age of the universe would pass many times over before such an event occurred. So the apparent irreversibility of nature, the reason things don't unmix and break or unburn, does not come from any one-way command written into the fundamental laws. It comes from statistics. If you start with an ordered system and allow random microscopic motions to take over, the system almost inevitably moves toward disorder, and that leads to a deeper, more unsettling question. If everything naturally goes from order to disorder, how did anything become ordered in the first place? Why is it even possible to begin with separation? Because here is the consistent rule of the world. Ordered arrangements tend to become disordered over time. A sharp boundary blurs. A neat stack scatters. A hot object cools. Order decays. Now, in physics, order doesn't mean beautiful or meaningful or aesthetically pleasing. It doesn't mean something you personally prefer. It simply means a special arrangement. In our tank, ordered means most of the blue molecules are on one side, and most of the clear ones are on the other. That's a specific configuration, a narrow possibility among countless alternatives. When they're evenly mixed, that's disordered, not because it looks messy, but because there are vastly more ways for them to be mixed than separated. You might like the mixed color better. That's irrelevant. Physics doesn't care about taste. It cares about counting. Now here's something fascinating. Suppose you walk into a room and see a tank where the left side is deep blue, the right side nearly clear, and there's a smooth gradient in between. You're told it has been left alone for 20 or 30 minutes. What do you conclude? You conclude that it must have been even more sharply separated earlier, because if left alone, it will continue to mix. The gradient will soften. The color will become more uniform. So, by observing the present state partially mixed, you can infer something about the past. The present contains a record of greater order behind it. That smooth transition from dark to light only makes sense if earlier the boundary was sharper, more defined, more ordered. And that insight is profound, because it means that whenever we see a system that is not yet fully disordered, we can reasonably assume it came from a state of even lower disorder, from something more special, more unlikely. This is how we reconstruct history. We look at the present and reason backward, not because the laws demand it, but because probability guides us. The arrow of time becomes visible not through equations, but through patterns of increasing disorder. And that brings us to the grandest scale of all. If every ordinary system we examine appears to have evolved from a more ordered past, then what about the entire universe? If things naturally move from order to disorder, then the universe itself must once have been more ordered than it is now. Which means the real mystery is no longer why cups break. The real mystery is this: why did the universe begin in such an extraordinarily ordered state in the first place? Because without that original imbalance, without that initial low disorder, there would be no arrow of time, no past and future, no memory. No story unfolding, just equilibrium and silence. If the water were not more sharply separated in the past, then in the time since, it would have become even more mixed than it is now. That simple reasoning gives us something remarkable. From the present, we can infer the past. We look at a partially mixed system and conclude it must once have been more ordered, because left alone, systems drift toward disorder, not away from it. Physicists, traditionally, don't spend much time thinking this way. Their usual game is forward prediction. Here are the conditions now. Here's what will happen next. Given positions and velocities, compute the future. But most other sciences play a different game entirely. Geology, for example. A geologist digs into layers of rock and finds certain fossils. From those fossils, she predicts that if you dig elsewhere in the same layer, you will find similar remains. She reconstructs an ancient world from fragments in the present. History works the same way. When a historian says, "The French Revolution began in 1789, he isn't just describing the past. He is making a prediction. He is saying, if you open another archive, if you uncover another letter, if you find another document that mentions that event, it will agree with 1789. He predicts consistency across sources he hasn't even seen yet. When someone says Napoleon existed, they mean that scattered documents, letters, military orders, diaries will cohere. They will fit together into a single organized story. So even when historians speak about the past, they are making testable predictions about the present and future discoveries. How is that possible? Why does the world preserve records in this way? The answer must be that the past was more ordered, in the statistical sense, than the present. There were clearer structures, sharper boundaries, lower disorder, because if the world had always been maximally disordered, there would be no reliable traces, no layered rocks, no fossil sequences, no consistent documents, no memory. Records exist only because the past contained special arrangements that have not yet fully dissolved. Now here's a provocative idea some physicists have entertained. Suppose the universe is in its deepest nature just random motion. No special beginning, no privileged starting point, just eternal chaos. If you wait long enough, even in a completely disordered system, tiny fluctuations can occur. With only a few atoms, you might occasionally see them accidentally arrange into something more ordered for a brief moment. That's called a fluctuation. So perhaps the argument goes, the universe has simply been going on forever in disorder, and at some point, by pure accident, it fluctuated into a more ordered state. And now we are simply watching that fluctuation unwind. In other words, maybe the ordered world we see, the stars, the galaxies, the history of life, is just a rare statistical accident in an otherwise chaotic eternity. How could we rule that out? You might ask, how long would you have to wait for such a fluctuation? The honest answer is unimaginably long. But here's the deeper issue. If the fluctuation were too small, if it didn't produce enough order to allow stars to form, planets to cool, chemistry to organize, life to evolve, and consciousness to emerge, then there would be no one here to notice it. We observe a universe structured enough to produce intelligent observers, which means whatever fluctuation occurred, if that's what it was, had to be vast, enormous, a staggeringly improbable dip into low disorder, and that raises the stakes. Because now we are not just asking why ink mixes, we are asking why the entire universe began, or at least once existed, in an extraordinarily ordered state. Why was there such a massive imbalance to begin with? Why wasn't everything already maximally mixed? Why is there an arrow of time at all? Every broken cup, every fading memory, every geological layer, every historical record, all of it traces back to that deeper question. The arrow of time doesn't emerge from the laws themselves. It emerges because the universe started in a condition of astonishing order, and ever since then it has been slowly, statistically, inevitably unwinding. Let's step back and think about this carefully. Some have suggested that the order we see in the world, the clear separation of stars and empty space, planets orbiting predictably, the layers of fossils in the ground, could simply be the result of a rare, gigantic fluctuation. a statistical accident in a mostly chaotic universe. And yes, in principle, a fluctuation could create a small patch of order somewhere. But here's the problem: if the universe is vast, and the atoms everywhere are mostly jumbled, then noticing order in one tiny corner tells you almost nothing about the rest. In fact, if a fluctuation is responsible for the order we see locally, it's overwhelmingly likely that everything outside our little region remains disordered. The odds that the entire universe would simultaneously fluctuate into order are vanishingly small. Think about an astronomer observing a distant star. If the universe's order were merely a local fluctuation, what should he expect when he looks at another star he's never seen? Chaos, random arrangements of matter, hot gas scattered without forming stars. No clear separation of matter and void. Yet every time we look, whether at distant stars, galaxies, or fossils buried in rock, we see the same pattern repeating: order, separation, structure, coherence. Even when predicting something we have not yet observed, the universe behaves as if it has been structured from the start. This consistency rules out the idea that our observable order is a tiny accident in an otherwise disordered universe. Instead, it suggests something far stronger: the universe, at some point in the past, existed in a far more ordered, less mixed state than it does today. In other words, to truly understand the irreversibility we observe, we need to add one additional assumption to the laws of physics: that the universe started or at least existed at some early time, in a highly ordered condition. This isn't just a minor tweak. It's a bold, time-directed statement. It explicitly distinguishes past from future. The past was special. The future is more mixed. And notice this assumption sits outside the ordinary physical laws, which are generally time-symmetric. The laws themselves say nothing about starting conditions. They only tell us how the universe evolves given a set of initial conditions. We can imagine that someday, astronomical history, the study of the universe's past state, could be considered part of physics itself. But for now, we recognize it as an essential extra. The arrow of time emerges not from the symmetry of the laws, but from the asymmetry of the initial state. And here's where irreversibility becomes tangible. To really see it in action, consider building a machine that is supposed to work in only one direction, something designed so that its motion, once started, cannot naturally reverse. By studying such a machine carefully, we can watch irreversibility in miniature, controlled example of the principle we see everywhere in the universe. It's the world's initial order, combined with countless microscopic interactions, that guarantees that some processes mixing, friction, decay will always go one way, never the other. The laws allow reversals. Probability forbids them. And that is the deep origin of the arrow of time. Let's bring this idea to life step by step. Imagine a wheel with a ratchet, a notched wheel with teeth shaped like little saw blades. A tiny lever called a pawl, held down by a spring, sits against the teeth. The design is clever. The wheel can only turn one way. Push it forward and it clicks over the teeth smoothly. Try to push it backward and the pawl jams against the teeth, stopping it dead. This is the principle behind winding a clock: irreversibility, built into the mechanism. Now, here comes a wild thought. Molecules in a gas are never still. They perpetually jiggle, bouncing off anything they touch. So imagine suspending delicate veins on the ratchet wheel inside a box of gas. Each molecule collides randomly with the veins, nudging them forward or backward. At first glance, it seems like you might have created a perpetual motion machine. The wheel should keep turning in one direction, powered only by the chaotic motion of molecules. But the devil is in the details. Every time the wheel turns, the pawl lifts to pass over a tooth and snaps back down. In that instant, the pawl could accidentally bounce, giving the wheel a tiny backward nudge. To prevent backward motion, the pawl must stick firmly when it falls. And sticking requires friction, and friction generates heat. Now, the plot thickens. As the pawl heats up from friction, it starts jiggling itself. The molecular motion inside the pawl increases. Eventually, the pawl is bouncing up and down so energetically that it no longer reliably blocks backward motion. When it lands, a tooth can slip either way, forward or backward. The very mechanism designed to enforce one-way motion can itself be reversed by the same molecular chaos it was supposed to exploit. Even more, if one side of the wheel is warmer than the other, the pole side hot, the vane side cooler, then the whole can actually turn backward. Driven by these thermal fluctuations, the incline of the teeth means that each pole bounce can push the wheel the wrong way. So here's the lesson: irreversibility at the macroscopic scale is statistical, not absolute. On the scale of atoms and molecules, the ratchet can fail. The microscopic world obeys reversible laws, and no clever design can escape that. Perpetual motion from thermal jiggling. Impossible. The molecular world ensures that everything eventually balances out. It turns out that no matter how cleverly you design the ratchet, it behaves predictably. If one side is hotter, it turns one way. If the other side is hotter, it can turn the opposite way. But once the temperatures equalize, once everything calms down to the same temperature, the wheel stops. It does nothing. And that's the subtle lesson. The one-way behavior of systems, the irreversibility we observe, only exists when things are out of equilibrium. When there's a difference, one side hotter, one side cooler, one side more ordered, one side less. It's this imbalance that drives change. At first glance, you might think that because energy is conserved, there's always as much energy as you want, ready to use. Nature never destroys or creates energy, it's always there. But here's the catch: not all energy is usable. Take the ocean, for example. The thermal motion of its atoms, trillions of molecules bouncing around, contains enormous energy. Yet, for all practical purposes, it's unavailable to us. To harness energy to make it useful, we need differences. Differences in temperature, pressure, or organization. Without those differences, the energy is trapped, present but impotent. Here's a simple analogy. Imagine you're at the beach, towels in hand, and a sudden downpour soaks everything. You grab a towel to dry yourself. It works at first. The towel is slightly drier than you, but the next towel is wetter and you're no better off. Eventually, all the towels are equally damp and you, too, are soaked. No matter how many towels you have, you cannot get drier, because the difference, the thing that allows energy to do work, is gone. In physics, the dampness in this analogy is temperature. When two things are at the same temperature, energy flows equally in both directions. No network is possible. The atoms jiggle, collide, and exchange energy, but nothing happens on a macroscopic scale. This is the principle behind irreversibility. If two objects at different temperatures are left alone, they naturally move toward the same temperature. Heat flows from hot to cold, order degrades, and the availability of energy decreases. But to objects already at the same temperature, they do not spontaneously split, with one getting hotter and the other colder. Nature does not reverse itself just because the laws permit motion. This is the essence of entropy. It always increases. Or, if you prefer, the amount of energy available to do useful work always decreases. Out of equilibrium, energy is harnessable. At equilibrium, it is trapped. In our ratchet example, this explains why perpetual motion fails. The fundamental laws of physics allow molecular motion to go either way. But the one-way behavior, the arrow of time, the march from order to disorder, is not a direct consequence of those laws. It emerges statistically from differences in energy, from systems striving toward equilibrium. Irreversibility arises not because the laws forbid reversal, but because differences available energy inevitably fade. In short, the arrow of time. The one-way flow we see in cups breaking, heat spreading, or ink mixing, comes from the gradual loss of usable energy, the relentless increase of entropy, and the fading of differences. The laws themselves are symmetrical. The universe is not. The effect we've been exploring, irreversibility, is far removed from the basic laws of physics. It's subtle, yet it governs everything we experience. Your memories, your personality. The difference between past and future, all of it is tied to this statistical arrow of time. But here's the striking part. Knowing the fundamental laws doesn't immediately give you understanding. The laws of physics, Newton's laws, Maxwell's equations, quantum mechanics are precise, elegant, and symmetrical, yet they do not directly tell you why cups break, why glaciers flow, or why ink mixes in water. Think about a glacier. You can watch it slowly creep down a valley, carrying rocks and shaping the landscape. You don't need to know it's made of hexagonal ice crystals to see it move. Yet, if you understand the microscopic structure of those ice crystals, their geometry, their slip planes, you begin to grasp the glacier's behavior. But even then, our understanding is incomplete. Nobody knows enough to predict every nuance, the important features of the world, the things that matter to life and experience, emerge from complicated interactions of many laws together. So, let's bring this all home. Why can't we reverse time? Why doesn't a broken cup reassemble itself? Why doesn't mixed ink separate back into color and clear water? Not because the laws forbid it. Every collision, every force, every interaction works perfectly in reverse. In principle, the microscopic laws are time-symmetric. The answer lies in statistics, probability, the overwhelming majority of ways for things to be disordered compared to the tiny number of ways they can be ordered. A cup can exist in one ordered state, whole, but there are millions upon millions of broken configurations. When the cup falls and shatters, it moves from one ordered state to one of countless disordered states. That's almost certain. For it to reassemble, for millions of atoms to randomly coordinate perfectly technically possible, yes, but so improbable that it will never happen. Not in the lifetime of the universe. Here's the deeper truth. The universe started ordered. The early cosmos was highly structured, low in entropy, finely tuned, and ever since it has been sliding downhill, statistically, inexorably, toward disorder. Entropy increases everywhere, always. This is the arrow of time. The reason you remember the past but not the future. Why causes precede effects. Why we age. Why things break but never unbreak. The fundamental laws themselves do not demand this. They are symmetric. Time could run forward or backward, but the initial condition of the universe, its primordial order, forces the flow of time in one direction. And that is the profound takeaway. The reason time moves, the reason we experience life as a sequence, is rooted in the universe's birth. The cosmos began ordered. From that, everything else, the flow of events, the irreversibility of daily life, the very sensation of past and future emerges. It's not just physics. It's the lens through which we see reality. Time flows because the universe once began in a way that made it flow. And that simple fact shapes everything you experience.